Okay. All right, let's get started. So today I'm going to start on a different topic. So we've been talking mostly about networks for the last, I don't know, 20 lectures. And now we're going to do distributed systems. The course says networks and distributed systems, so I guess we're going to do a little bit of that. But as you can see, most of the course was about networks, and we're going to actually do a very high-level view of distributed systems. And the reason is because we've actually seen distributed systems already. Distributed systems are, in fact, the application layer. So what I'm going to talk about today is really like a high-level view of what is a system anyway. I mean, when we talk about systems, what are we talking about? Why is it important? And then we talk about the context for distributed systems, and I'll put it in the context of what we've studied so far in terms of networks. And then we'll go into a bit about motivation for distributed systems as opposed to centralized systems, and some properties at a high level. And then the remaining lecture, the last part of this lecture, I'm going to talk about one particular aspect of distributed systems called locking. And you actually probably run into this already if you're doing any kind of threads or processes for the third assignment. You run into locking already. Okay, so hopefully the discussion on locking is going to help you with that. And then in the remaining 3 lectures, what I'm going to do is to go over some more algorithms used in distributed systems, what's called leader election and consensus and so on and so forth. So we'll look at those later on. We're going to start with the first part over here. So just like I started out by saying, what's a network? Maybe I'm going to start by saying, okay, what's a system? Okay. What is it? You've seen the word system used perhaps in many, many different contexts. We talk about biological systems. We talk about network systems, computer systems. What's a system? Yes?
A bunch of programs together that interact with each other.
Bunch of
perform certain functions. Or add functions.
Okay, so bunch of programs that, maybe I should write this down. Bunch of interacting programs. Maybe I'll call it set. It sounds more mathematical than to say bunch. Set of okay. So Ryan?
I would add to that it takes in a particular input.
Yeah.
And gives back a particular output.
Okay, with specific input and output. Okay. Anybody else? That's it? That's all? So a biological system is a set of interacting programs too? A chemical system is interacting programs as well? Clearly not. Yes?
A set of components that can interact with each other and provide some kind of functionality.
Okay, interacting components with specific input outputs and providing functionality. Okay. Anybody want to refine that? So this actually is pretty good. I mean, this is about as close as we're going to get to defining a system. Yeah, Clarence?
The components are self-contained.
You're going to get into big trouble when you say self-contained. What does it mean to be self-contained?
Each component is like independent of the other, but they still need to interact.
Yeah, so maybe what you're saying is each component has a well-defined interface.
Yeah.
Right. So, okay. Okay, so that's actually even better. So you have interacting components. The components have well-defined interfaces, and then the whole system has a specific input-output. And actually what you can think of is that the whole system is providing an interface as well, right? And so what we have in Notion is that system actually is composed from components or subsystems. So you take something small, you put an interface on it, and then you build it into something larger. And we've actually seen this already. When you take the network layer, it has a particular interface to it, which is give me a packet with a particular destination address, I'm going to deliver it, right? And the transport layer says, give me a stream of packets, I'm going to make sure it's reliable, and so on. So what we're really doing is we start off with what we can think of as a component or a subsystem. And we put on top of it an interface, which, and I'll get to that in just a minute, what it is exactly. And here's another component, subsystem, or interface, etc. And then what we do is we put some GUI around it, okay? And on top of that, we slap on an interface, like so. And that whole thing we call a system, okay? That's really what it is. And it has some input. And to be more precise, we'll call this a service interface because we can think of what it's providing as functionality. We'll call that a service. That's really what it is. So let's take a very specific example, right? For the assignment 2, you had a client-server tic-tac-toe program, right? What was the tic-tac-toe program doing? It was using underlying components. The components that you had over here were computation. You use computation to compute. You use computation to compute whether the board was done or not, right? Is somebody won or not? That's a bit of logic. That's computation, right? It's a processor executing that. You had some storage, which was the board, right? The board was this memory allocation is saying this was going on. Plus, you had one more component. What was that? Yeah.
Players?
No, players are not, they're outside. They kind of participate. The client is on the other side, right? What is the server doing? What is the other thing the server needs to do? It needs to compute something, it needs to store something, it needs to, the server isn't displaying anything per se. It's just communicating with the clients, right? So we're talking about the servers. Beg your pardon?
Is it like sending it to the other side?
Sending it, so what's that called? Communication? Yeah. So communication. And in fact, these three elements, computation, storage, and communication, which you can think of broadly as the term resources, are really what any computer system is going to be working with. Any computer system can be essentially decomposed into computation, storage, communication. You can take it up, we can decompose into these three parts. And so these components or subsystems are providing some kind of computation or storage or communication or something together, or something that combines those things together. And then we take all this and we put a service interface on top of that. So we have some element like a disk is going to provide you storage service, okay, the disk system if you want. The memory system is going to provide you storage service. The network interface card is providing you a communication service, okay. The CPU is providing computation service. So we take these services, which are these little components over here, and then we use those service interfaces to compose something, in that case, in this case, a tic-tac-toe program, and then you expose a service interface which is different from what you had from below, right? The different one over here is you can play a game of tic-tac-toe, right? The same approach would be used by, let's say, Facebook, right? If you take Facebook, okay, unlike the two-player tic-tac-toe, it has 200 million, sorry, whatever the number is today, 800 million users. But if you think about it, at the bottom, it's still the same, okay? They're doing some computation, okay? Who are your friends? Okay, so you have a query, a request that goes in over here that says, who are my friends? And you get a response. My friends, your friends are so-and-so. That information is stored in a storage system, okay? And then there's communication, which is exposing to you the set. So when you are using, let's say, less complex example, let's take BitTorrent, for example. Okay, BitTorrent is a bit less complicated. So here you have the tracker, which is providing a computation service. It's saying who are the people I'm supposed to be exchanging torrent files with. And then you have local storage, and you have communication with your neighbors, right? So you can take any application, any system, actually decompose it into these three different elements, okay? This is true whether it's distributed or centralized. It's just any system is going to have this. However, with the distributed system, we are going to have a little bit more to it, and I'm going to come to that in a moment. But before I do that, any questions about this so far, what a system is? Okay. So similarly, if you look at a biological system, you have you have sort of the subcomponents, your digestive system, you have your nervous system, etc. And all of these, you have an overall system, right? So you kind of bring these things together. Okay, so let me talk about the context. What I mean by context is really how this fits into what we've been looking at so far. And to do that, I'm going to redraw this stack that we've been looking at. So we started out with this application layer. And then below that, we had the transport. And below that, you have the network layer. And then we looked at link layer. And then security sort of sits off on the side, okay? Because it's true, it shows up at all these different layers. Where would a distributed system fit in? Where would that fit in? Yeah, application layer. So that's right. So the distributed systems typically are not typically, are pretty much always implemented at the applications layer. And we've already studied some of them. BitTorrent is an example. DNS is an example. These are all application layer. So distributed systems, in some sense, is just a way of studying specific techniques, algorithms that can be used in developing network applications. So distributed system, you can say, is equal to a networked application. Okay. All right. So let me give a little bit more kind of a perspective on what a networked application might look like. So I'll start off like this. So when you have your own laptop or PC that's not connected to the internet, we can think of it like this. This is just a point. And if you're at this point, you're at your laptop, you can use computation, you can use storage, but if you're not, you can't, right? A client server is like a line connecting 2 points, okay? This is the client, this is the server, and it's like a straight line, okay? Basically, you just talk to one server, and that's it. Again, your tic-tac-toe program, an example of a client server. With a distributed system, it's more like a plane. So imagine that you're looking at the front page of, I don't know, let's say pick something, Yahoo front page or whatever, your Google, whatever the thing is called, I page. So you have a website over here, and it has these little components from all over. There are ads, there's news, there's weather, there's other stuff going on. Each of these is being delivered to you from some other location, right? So what this actually looks like is that you go to, let's say, Google, and this is actually fetching stuff from a different sort of other points, which might in turn be fetching stuff from other points, and this might be coming from some content distribution network. And all of this is to just give you one page, right? So this doesn't look like a line anymore. It looks more like a tree. Or if you want to be geometric about it, it could be a plane, I guess, in the limit. But that's what a distributed system looks like when you look at it. Okay, it doesn't look like you're talking to one single server. You're actually talking to a bunch of different things. And if I were to draw a BitTorrent, it would look similar like this. Similar. I have a tracker, except then I have these direct communication to these tree of other nodes. So essentially, we have a point to multi-point set of communication, and that's what makes something into a distributed system, as opposed to this. This is a centralized system. This is a client server. And this I would call a distributed system. Okay, so that's basically the difference. So when we have a distributed system compared to a centralized system, things can go wrong quite easily. Okay, and so I'll give you a motivation, then we'll take a break, and then we'll look at how to solve this problem. So I'm going to take a specific example of a shopping website or shopping. Let's take something like Amazon. So I have, let's say, a warehouse, and I have in there, some things that I sell, some widgets. I have n widgets that I want to sell. So what I'm going to do is I'm going to put a storefront on it. Storefront website. Okay. And then I have a client over here. And the client goes to the storefront website and says, I want to buy, whatever, 20 widgets. And the storefront site needs to check with the warehouse, are there 20 widgets available? Maybe there are only 10 available, right? If there are only 10 available, you can't sell 20. So it's going to make a query saying, how many widgets? That's a request. And you get back a response, 20. And then it says, yeah, 20 is OK. You can buy it. Life is good, right? Now, let's assume that we actually have a storefront website that's replicated, because it's a content distribution network. So we could essentially have two storefronts, and this has got the same kind of thing. And this has some other client also coming in. Okay. This is not a site front, it's a storefront. Okay, so let's see what might happen in this case. So the client says, I want to buy 100, whatever, some number of widgets. How many? It says here 20, okay. This comes in and asks, how many do you have? If that sale has happened, then it reduces it by 20. It says, this is how many I have. And then it's okay. Life is good, because you're never going to be an inconsistent state. What does inconsistent state mean? It would mean something like this. Let's say the algorithm was, it says, how many do you have? It says, I have 20. And it says, OK, I want to buy 20. Now this guy comes in, how many do you have? I have 20. I want to buy 20. But when this buys 20, that answer is no longer valid. Okay? At that point, it doesn't have 20 anymore. It has 0. So when it says, I want to buy it, it says, oops, sorry, I don't have any. Okay? That's not nice. Okay? So what's going on is that this, if it were a centralized system, there's only a single storefront site, only one warehouse, there's no problem. This won't happen. Because you ask this question, nobody else can get to the warehouse except this one over here. But the minute you allow two front ends to talk to the same back end, if you aren't careful, you can get into trouble, right? Because the first one says how many, it says 20. What the warehouse has to do is to say, when this asks how many there are, it shouldn't say I have 20. It should say, I just gave somebody 20. Potentially, I'm not going to have 20. Okay? So let's think about that for a moment by drawing this timeline of how things would happen. So the request comes in, you say how many, and that's from the first one, and you reply back 20. Okay? Now the second request comes in from here saying how many. Okay, and let's say you had n over here. Now the answer could be either 20, sorry, so you have 20 over here. You could say either 20, okay, or you could say, look, I just told this guy 20, and maybe he's going to buy all 20. I don't know, right? So I'm going to reply, maybe I'm going to say 0. Because somebody just asked, maybe I want to say, so how many, it says, I want to purchase something. I want to put, At this point, we have a decision to make. When somebody asks and says how many with the intention to buy, right? Should you say, okay, I'll just tell you 0, it's conservative, right? Or you can say 20, because you could be optimistic in the sense that you think the sale isn't going to happen. I guess it's pessimistic, but anyway, you see the point, right? It's one or the other. And in fact, systems differ in how they work, right? Some designers say, look, I'm just going to tell you whatever I actually have. If it hasn't been sold, it hasn't been sold. So what could happen is that we could have this person come in, get back the answer 20. The other person comes in, they have 20, and then they say, we want to buy 20, and this comes back over here and says, I want to buy, sorry, we're all sold out. And this is what happens with airline systems. If you go to airline system and you make a reservation, it's exactly like this. They have N seats on some flight. You have storefronts, which are your website. Okay, the seller, Expedia is selling it, Travelocity is selling it, the airline's own website is selling it, and they all have to go to the same back-end warehouse. And if you make a reservation on a flight and you take too long, you can find that they'll say, oops, the price just went up, or the seat is no longer available. Because at that point, when you ask how many seats are available, I need 4 seats or 6 seats, whatever, it isn't locking it down for you. It isn't saying, no, you have it. It's just making like, okay, I have so many, but if anybody else acts faster than you, you lose it, right? Some other things act differently. They say, okay, if you're going to take 20, you know for sure you're going to have those 20, okay? And so that's what's called optimistic versus pessimistic approach to replying to this answer over here. And this is never going to be a problem in a centralized system. In a centralized system, when you have only one storefront, one warehouse, we're never going to have this problem because we have one single view of the world. What's going on is that we are now getting 2 different views of the world, and these views of the world may not be consistent. Okay? And so what this means is that we have this property of inconsistency. And this inconsistency arises just because it's a distributed system. If it were a centralized system, we wouldn't have it. Okay? So is that clear? So anytime you have, what we have over here is, we call this concurrency. Okay, concurrency over here, we can have inconsistency because they may have different views of the world. Similar problem, by the way, can happen with, let's say you and your friend decide to go to ATMs at the same time, and you both have the same ATM card. Okay, it's possible. My wife and I have the same ATM debit card. We could potentially coordinate with each other to go to an ATM at the same exact moment in time, right? And say, okay, I want to withdraw all the cash in my account. And she goes and says, I want to withdraw all the cash in my account at the same time. Okay? So the bank says, okay, you have a credit card, all right. Debit card, I want to give you whatever, take all the cash out. I do all the cash out. We both get the cash out twice, and then we leave the country. Okay? Now, we wouldn't do that, but potentially you could. Okay? But remember, leave your cell phone at home when you do that. Okay? Okay. So we have the same exact problem over here. The bank has to make sure that you can't have these concurrent withdrawals in such a way that they're going to lose money. So how do they do that? They have 2 techniques of doing it. What do they do? I'm sorry?
Sorry, I can't remember. But I remember.
Two-phase locking? Yeah, we'll come to that later. But one is that they kind of, when the first withdrawal is about to start, it basically is pessimistic. Because I'm going to assume this withdrawal is going to terminate. I'm going to assume that all that money is gone away. So the second person asks for withdrawal, it's going to say, look, I have a withdrawal in progress. I'm going to assume it's going to complete, so I'm not going to give you the money. Right? That's the first thing they do. The second thing they do is they limit your withdrawal to some number, I think $300 or $1,000, whatever it is. And they say, okay, if they break into the system, we only lost $1,000. That's how much profit we make every nanosecond or a week here. So that's the other thing that they do. Okay, so I'm going to stop here for a moment, and we'll continue with the distributed system properties. Okay, so I'm going to now continue with this, a little bit of motivation for why do we want to make distributed systems in the first place, right? And this should be relatively straightforward. We kind of have studied this already, so it's more of, I guess, reminding you of it. So our alternative to a distributed system is a centralized system, right? And so we want to say, what is the motivation for distributed systems? So why? Why would you want to do it? Yes?
Centralized system can't scale.
So we want scalability, okay? Okay, what else? Why else would, yeah?
Centralized system has one point of failure.
Right, so you want to have basically fault tolerance. Okay. What else? Yeah.
Load balance.
Load balancing. So that's scalability, right? So we get scalability through load balancing. Yeah. Okay. Anybody else? There's one more reason for distributed system. Let me try and motivate that. Remember with DNS, what do we do with DNS when you have a big central thing? We hand over part of this namespace, right? Each namespace hands over part. What's going on with that? What's that called? Yeah? Sorry? Delegation. So why would we want delegation? What's the advantage of delegation? Yeah, it helps scalability, but it's more, okay, why would you want delegation, right? Here I have a system where there's no delegation, and another system which has delegation, so what's the advantage? Yeah, William.
You can make it more local. So
more local. So you can basically, you can give local control, right? So we don't need to check with the, you don't need to check with the big boss about what needs to be. I don't need to check with the president of the university what I'm going to teach in each lecture, because they've delegated that to me. It would be impossible for the president to sit there and kind of manage every single lecture in every single class. But delegating that power to me, I have local control, plus it scales as well. So you get two of that. And to some extent, one could say localization. I'm going to put that in. We can make centralized system localized. But it's much easier to do localization when you're distributed, because if you want to have let's say a storefront which is in one particular language, which is for one particular culture, one particular country, you'd rather just do that in a distributed system than to have that in the centralized system. Okay, again, in a centralized system, when you go to some website, it'll say, click here if you're from this country, click there if you're from that country. It's much easier to just do it with localization, just have a local storefront, and then you basically have it in the right format already. Okay, so these are some of the motivations for distributed systems, but the problem is that they come at a cost. It's not free, and so we have a set of problems that arise because it's distributed. We already saw one, which is possibility of inconsistency. Okay, and there are a few other problems as well. So instead of looking at the problems, I'm going to actually flip it around. And I'm going to look at what are the properties we would like to have in a distributed system. Okay, what are the things? So let me just change this around and say there are some desirable properties. And we'd like to maintain these desirable properties. I'm just going to write these down, and then we'll go through them one by one. So let me just and I'll go through them in order. Okay, so we have a whole kind of laundry list of properties over here. I'm going to go with them quickly, and then I'll go through each of them a bit more detail. These four properties on top are often called the acid properties. And this stands for atomicity, consistency, isolation, durability. And the acid properties come from distributed databases, which are a very important class of distributed systems. So if you take a database course or you're using any kind of distributed database, this is the kind of properties we really emphasize. I'm going to go through them because they're very important. Not all of them apply to all distributed systems, but it's good to know what these mean. Then the general distributed systems, we'd like to have these properties: fault tolerance, which is exactly what we want from the system; scalability, synchrony, which has to do with time, the notion of time. Or more precisely, it has to do with the notion of what happens before, what happens after. So that's important. And then transparency, performance, and heterogeneity, which have to do with how we build a distributed system. Okay? And we'll talk about more of those in just a moment. So as I said, today's lecture is basically going to be about these properties, what they mean, okay? And we'll use examples to look at these properties. And then the remaining lectures, we'll go through some tools we can use to achieve fault tolerance, to achieve scalability, to achieve synchrony, and so on and so forth. And there are many, many tools, and we're just going to go over it at a higher level and until we run out of time. So that's basically what it is. Okay, so let me start over here with this notion of these four properties called the acid properties. And so the notion we want to have here is exactly that of we have a central warehouse, okay, or a database to be more. So we have a central database, and it has some request and some response, like we saw before, except that we want this request and response to have a particular form that we call a transaction. Okay? A transaction is essentially either reads the database, or it writes to it, or it does some combination of reads and writes. Okay, so that's basically it. So the basic transaction would be, I want to know how much money I have in a checking account. So that's a read transaction. I do a request, what's my money checking account, I get a response. Okay, that's simple. A more complex transaction would be this. I want to transfer money from checking to savings, right? So I have a read of the I have to basically let's say I want to transfer, let me just write this down. I want to transfer $200 from checking to savings. So what are the components over here? We have, first I want to read the checking to make sure I have $200 in the first place. If I don't have $200, I can't do this, right? I need to then write to the savings. I have to write in savings the new amount, and I have to write in the checking the new amount, right? Those are the three things. Now, what I want to do is to make sure that all these three things all happen or none of them happen, right? It would be a problem if my savings account were incremented by 200, but the checking account were not decremented, because that means I just got $200 from nothing. And the opposite is bad too. If I were to write to savings and not write to checking, that wouldn't work either, right? So all three should happen, or none of them should happen. Okay? And so a transaction is a way to group a set of operations together such that they all happen or none happen. Okay? So that's a transaction. These three things together is a transaction. And atomicity is this property of transactions, that they all happen together like an atom. Yeah?
Sir, can you just repeat what you said?
Sure, that's fine. So I want to, this is my bank account, let us say, or I have a checking account and a savings account. And I want to transfer $200 from checking to savings, right? So the first step is I want to read the checking account to see, do I have $200 to transfer in the first place? If I have only $20, I can't transfer $200 to savings, right? Then I want to write to the savings account the fact that it's incremented by $200. And then I want to write to the checking account that it's gone down by $200. That's how transfer happens.
But why does the two writing processes have to happen at the same time?
Not at the same time. They have to happen one after the other. But I want both to happen or neither to happen, right? These two things, either they must both happen or both of them should not happen. But I can't have only one succeed. Okay? And that's what's meant by a transaction. A transaction is a way to group things together. Okay? So an atomic transaction is one that has this property that either the transaction completes or the transaction fails, but there's no intermediate state. Okay? And this is true for very many different things. Right? The warehouse example, when I want to buy something, I have 200 widgets, I could put it in the transaction, say, okay, you're going to inquire how many widgets you have, and then you're going to buy it, and I'm going to put all of that in the transaction. So at that point, either you inquire and buy, or you don't inquire and don't buy, but you don't have anything in between. Okay. Everybody clear on that? So that's meant by atomicity. Okay? And in a distributed database, it could happen that I have one computer over here, which is my savings account, savings database, and then I have a checking database. And they're separate computers, and they're talking on some network to each other. So I have some system built like this, and then on top of this, I have my request response. So it's not obvious that these things are going to complete at the same time, because I could have a completely separate systems. I could have a savings database in Toronto and my checking database in Montreal, for example. Okay? There's no reason why I can't do that. And so this read-write things could actually take certain amount of time. It would take 20 milliseconds, it might take a second or two. And during that period of time, it might fail. It might happen that the savings database actually has a power failure and it goes down while you're trying to do the write to the savings account. And so you do read. So in a centralized system, the thing crashes, for example. Okay, you can recover from it. When you have a distributed system, it's possible that you have inconsistencies and so on. So the property we'd like to have is that of atomicity. So we say if this distributed system is atomic, I put enough logic into it so that we can guarantee that the transaction is atomic. Okay, does that make sense? Okay, so that's the first part for desirable atomicity. Okay, so the second property is that of consistency, and we'll keep the same database over here and look at consistency. Consistency has lots of different meanings, but in the perspective of the database over here, we can say that there's a property of the property is that after a transfer, okay, checking amount plus savings amount, is the same. Okay, so that's the consistency property we define for the notion of a bank transfer. Okay, so the amount of money that you have in checking plus savings is going to be the same. And so the database is said to be consistent, or distributed system is consistent, if the consistency property is always true. Okay, so the consistency property of the database here allows us to guarantee that after a transfer you didn't lose any money or gain any money. Okay, of course, in this particular simple example, consistency is achieved because of atomicity. Okay, they happen to be the same, but there are more complex cases where you have atomicity but don't have consistency. Okay, in a general distributed system, if you take a look at, for example, for Facebook, you can have consistency in a different way. So can somebody think of an example of a lack of consistency in Facebook? What would be a lack of consistency in Facebook? Yeah.
Post a message to someone's wall, but someone else who should see that message on the wall does not see it on the wall.
Exactly. So your view of what the wall is and the other person's view of the wall is inconsistent, right? That would be, for example, an inconsistency in the Another thing would be that you might declare somebody to be a friend, but they don't declare. It's not whatever. It's supposed to be bilateral, I assume. So it's not actually it's not symmetric. But in any distributed system, we have this problem. I mean, particularly bad form of consistency is you go to the web store, website or something, you buy something, okay, and you pay them the money, and then they say we don't have any record of it. We never happened. As far as we're concerned, you never bought the thing, and you have and so that's a very bad situation, right? So you go to Amazon, you buy a book, and 2 weeks later you have no book. You say, hey, I bought this book, and they say we have no record of it. Can you prove it? Well, not really. It is on Amazon. You guys own everything. So consistency is super important if you want to preserve the reputation of the shopping site, for example. Okay. The third property is what's called isolation. And isolation basically means that going back to this database, that things don't collide with each other. So isolation means that if I'm doing some transaction from here on my savings and checking, and somebody else is doing some other transaction on their account, okay, these two things shouldn't interfere with each other. Okay, so just because I'm moving money around from checking and savings, it should not be affected by whatever else is going on. Okay, the rest of the system could be doing whatever. I don't really care. I just want my stuff to happen independent of everybody else. Okay, and that's isolation. I'm isolated from the rest of the system. Okay, and again, obviously, it's a good property to have. Now, why would this not happen? For example, you might be doing your transfer from checking to savings. The example over here, but there's a lot of other load going on, and because of that, the system crashes. Okay. You're not isolated. Okay, if your transaction fails, if your work fails because somebody else is causing a load, that's not good. Isolation actually is a problem in network systems all the time, right? Can you think of an example of where we don't have isolation? Okay. So remember okay, let's try somebody else other than Clarence for now. So what I want you to think about is this. You're trying to get access to a distributed system, and you can't get access to it because of somebody else. Okay, what would be an example of that? Yeah, Victor.
Okay, let's say you want to connect to World of Warcraft, and
yeah,
you have like a lot of people in the server, so you
yeah,
have to wait.
That's right. So another example, so World of Warcraft, if you have a lot of load on the system, you can't connect because there's a lot of load. What else is an example? There's this particular kind of attack that you may have studied. Yeah.
Distributed service attack.
That's right, denial of service attack. Denial of service attack is exactly a loss of isolation. What's going on is that we want to go to a particular site, but there's a flood of requests from all the other users or a robot bot farm, as they call it. And consequently, you can't get access to that service. So obviously, you don't have isolation over there. Okay, so that would be a loss of the property. And finally, durability. Durability means that once something happens, it stays happened. Okay. So imagine that you go to your bank and you transfer the $200 from checking to savings, and you come back the next day and it didn't transfer. I mean, it undid itself. You say, wait a minute, I thought I did that yesterday. Oh, no, you didn't. Okay, it's gone, right? You have to go and do it again. That's a durability problem, right? And durability is, of course, it's a very good thing to have, right? You don't want to be in the situation where you have something that just got to happen to be undone, right? You're using, for example, the Learn website to turn in your assignment. You turn in your homework assignment, and you come back the next day, it says, it's gone. Okay, the computer ate my homework. Okay, that's lack of durability. Okay, so again, we want to have durability. So if something happens, it stays happen. Now, why would you lose durability? Again, typically because of failure. So let's say that the Learn website is using some database somewhere, and that database is sitting on some file system somewhere, right? And that file system is getting backed up perhaps once a day or once an hour or whatever. You turn in your homework, it gets stored on the file system, and then there's a big power outage. your file system goes down, your disk crashes, and they're going to restore it from the backup, but the backup doesn't include your assignment. Well, at this point, your homework is undone. So unless you're very careful, you can lose your work, right? And that's exactly what durability wants you to do. So if you have a system that's guaranteed to be durable, then everything is fine. Okay? So these properties of atomicity, consistency, isolation, durability are sort of bread and butter properties that you'd like to have in any, certainly in any database, but also in distributed systems. Yeah, good.
So durability is kind of its ability to maintain state
Maintains.
crashes.
Or despite crashes, correct. So you always have an increment, you never go back in time. Okay? So like if you're using Piazza, which is another distributed system, you write a comment, that comment is going to stay there. It's not going to vanish after some point in time. Right? It's going to, yeah.
So if our tic-tac-toe program like wrote to file,
right,
it would then be more durable.
It would be more durable because if it were to crash, then it wouldn't have lost the state. Right? Of course, but the file itself may be corrupted, or the disk may crash, and so on. So providing these properties is actually quite hard. Okay? To make a system that is atomicity turns out to be quite easy to do. Okay? It was thought to be hard, but it is really quite easy. Consistency, it depends on what kind of rules you define. If you define reasonable rules, it's relatively easy, but if you want to be more complicated, it's very hard. Isolation is almost impossible to provide. Okay? Because if you have enough load on the system, things are going to slow down. Right? There's no real way for me to provide perfect isolation. So this is almost never achieved, okay, in terms of load, in terms of performance. In terms of correctness, yeah, but not in terms of performance. And durability, we try very hard. Okay? And we almost always succeed, but not always. There can always be this, this kind of pathological circumstance where we don't have durability. And that's why it's always a good idea to print out your receipts, so that you go back and say, oh, you actually sold it to me, and they say it's not there, then you say, no, look, I have this printout over here. So, of course, you could have photoshopped it, but that's another story. Okay. Any questions about these 4 properties so far? Okay, so I'll take a break here, and we'll come back to these other properties, and then we'll look at something about locking. So these 2 properties of fault tolerance and scalability are kind of why we started doing distributed systems in the first place, right? So we want to have fault tolerance because we want to have avoid the problems. But for fault tolerance, it's an easy thing to say, but really the hard part of fault tolerance is defining the faults that you want to tolerate. Okay, what are the faults, right? And this is where it gets really hairy. If you can define the faults, then tolerating them is relatively straightforward. I mean, it's not cheap, it's not easy, but it's relatively straightforward. What gets you is the faults you can't define. Okay, so what can the faults be? We can define faults to be like a link failure. Certainly, we can talk about that. That's an obvious thing. We can have a computer failure or a node failure. We can have a disk failure. Okay, these are relatively easy because remember the underlying system is providing you communication, computation, and storage, right? So if these things are failing, then we have a failure. It's easy, but we can have other kinds of failures. We can have a packet corruption. Okay. So that's not a failure really, okay? It's just that you got wrong stuff coming out of it. It can be insidious. You can have a computation that's incorrect. Now this is a really tough one. Computation is incorrect. So you take 2 numbers and you say, add them up, and the computer gives you a wrong result, because there's a bug in the hardware. How are you ever going to find, how do you tolerate that fault? Right? How do you tolerate that fault? That's a pretty complicated fault to tolerate, right? And in fact, around 1995, I think, Intel had the Pentium chip, which had exactly this problem. On certain computations, it would give the wrong answer. It was just wrong. And people were completely aghast because they had no way to check that this was working. So the one way around this, okay, if you really care about it, one way around this, and this is what some people do, like NASA does, because imagine you're sending a spaceship to Mars, okay, and 1 year, or it takes 2 years to go there. 1 year after you send the spaceship to Mars, which is using a processor, the manufacturer announces, oops, we just forgot to tell you that if you add these two numbers or if you add these things, the answer is wrong, okay? You're going to lose the whole mission, right? So what NASA does, not for all systems, but for the critical systems, is to buy 3 different processors from 3 different manufacturers, okay? And it's completely, each system is coded by a different team of programmers and so on, and then they vote, okay, with each other, and then the winner, the person who, the computation which 2 of them come up with the answers to be the same, that's the correct, it is assumed that's correct. You assume that 2 manufacturers aren't going to mess up, okay? Of course, the voting system it can fail. Then you're in trouble, okay? You have to trust that the voting system is absolutely, completely correct. And however, the voting system is kind of small, so you can verify that more easily than verifying the underlying system. So that's what, but this is a very, very difficult thing to catch computation correct. And of course, we can have this corruption. So you have a file, and you read from it, and guess what? The file isn't the same anymore. So these 3, packet corruption, computation corruption, and disk corruption, are basically the same as these 3. Here you have failure, right? And these 3 are not quite failures, but things are not quite right, okay? Now with packets, we do a lot of work to make sure it's fine. With computation incorrect, we actually don't do anything. We just assume it's going to be okay. And if it's disk corruption, we do have the same idea as packet corruption. A disk is just a frozen packet. You can think about it, right? If you take all the bits in the packet, whatever you do for packet corruption, you can do for disk, and for memory, for that matter, corruption. Okay? But these faults, again, don't completely cover the spectrum of possible faults, because what gets you is not individual faults, but combinations of faults. Okay? So you could have a simultaneous, for example, computation incorrect and a packet corruption. So you do a header checksum, but the packet is corrupted, however, the computation is incorrect too. So you say it's fine. Okay? For example, if you just do parity, we're counting up the number of bits. Okay? It has to be even or odd, right? And it turns out that the computation which did that was also wrong. So we have both of these, and we couldn't even find out. Similar kind of problem happens with computer failures when you have a synchronized mass failure. So you say, look, I have 2 computers, and one is a primary, one is a backup. So the primary fails, the backup is going to take over. What happens if they both fail? Then you're out of luck. But you say, well, it's very unlikely, because computers fail once every 3 years. So the probability that both fail at the same time is very, very low, except if you have a solar storm, right? Like we had 10 days ago. If you have a big solar storm, it's possible that all the computers in Ontario go down at the same time, and all the networks too. Okay? Then what do you do? Okay? Well, what you do is you basically learn to cook, okay, from what you catch and or what you grow, because nothing is going to come up again. Similar kind of fault tolerance problem was in Fukushima, right? So all of you saw that what happened a year ago. So they said, well, if the reactors fail, we'll use the diesel generators. And if the diesel generators fail, we'll use a battery, whatever. But they never thought that they would have a combination of an earthquake and a tsunami, okay, at the same time. They just didn't think that you had a combination of failures. And the problem is that if you have n failures, you have n square pairs of failures, you have n cube triplets of failures. It's just too many. It's impossible for us to design and build for combinations of failures, so we just hope it doesn't happen. If it does happen, we're basically out of luck. And so now 100,000 people in Japan can't live in their homes because we had a combination of failures. And in that case, it was a reactor failure and a diesel generator failure. But we could have similar situations if you have an electromagnetic pulse that destroys computers. Okay, destroys computers and storage, etc., over a wide area. So we are actually very vulnerable to these kinds of failures, and very little can be done about it. Okay, the more reliant you are on computers for your daily life, the more exposed you are to these kinds of faults. And this is an area where we are at risk. Okay, as a society, we are at risk because we're depending more and more on these systems to be working correctly all the time. And part of the reason for the whole Y2K scare, maybe you guys are too young to remember the Y2K. Were you in school even at that time? 12 years ago. How old were you in 2000? 10. Okay. You guys don't even remember. Okay, there was this big thing called the Y2K scare where they thought that all computer systems would fail. Like people would get stuck in elevators, planes might stop flying, and so on because of a coordinated computer failure. Okay, and I was, of course, old enough to remember this. But the first developed country to hit this was New Zealand, I think. And so the whole world was watching New Zealand to see what would happen. And people like, okay, we're not flying, we're not taking elevators, we're just going to stock up on canned goods and wait and see what happens. And nothing happened in New Zealand. It was actually nothing happened. Either they fixed all the bugs, or there weren't that many bugs to begin with, and somebody did a marvelous sales job on Y2K. But at any rate, what happened was that nothing happened. But that doesn't mean it won't happen again. It can happen later. Okay, so that's fault tolerance. Scalability basically means that we want things to grow without bound. Again, we know that scalability per se is impossible, right? We can't grow without bound forever, but certain things can. If you throw enough resources at it, you can. We saw how DNS can basically grow forever. There's no reason to have any limit on DNS. And all systems that are patterned on DNS, content distribution networks, peer-to-peer networks, and systems which use load balancers and multiple locations, like Facebook and YouTube, Google, Amazon. These kinds of systems actually have been designed from the start to be scalable. Okay, and so we know what to do. We know how to build these systems to make scalability happen, and that's actually a very big success story, right? I was reading this article just a couple of days ago, which really brought this to bear, right? It said that a Maasai tribesperson with a cell phone, okay, Maasai tribesperson with a cell phone today has more communication power than the President of the United States had 20 years ago. Okay? Because 20 years ago, 1992, very, very few people had cell phones and mobility, and they were not in self-towers and so on. But today, Maasai tribesperson, probably the least developed part of Kenya, is able to have more power. Even more impressive, if they have a data phone, okay, data plan, and they have a smartphone, and they can access a search engine, Google or Bing or whatever, they have access to more information than the president had 15 years ago. Okay, the President of the United States presumably has access to the most information in the world in 1997. This tribesperson has more information. They have Wikipedia. They can look up anything they want, anytime they want. Okay, but between Google and Wikipedia, we have been able to build essentially scalable systems. And for example, Britannica just announced that they're going out of business. There's not going to be any more print editions of the Britannica. Now, again, you guys don't remember these days, but I used to have access to a print edition of Britannica. It was about this 17 volumes. It weighed about, 200 kilos. Okay, and you had to look through it. And no hyperlinks. You can't click on anything. Actually, you have to read through the stuff. Because of scalable distributed systems, okay, that's gone away. It was around for 200 years. It just went away because Wikipedia, which is volunteers sitting around using a computer distributed system, just blew it away. And they did it for free, okay, essentially. So that's amazing. Okay, let's go into this one, synchrony. So these two we saw here. Synchrony basically means that the different components of the distributed system agree on time, okay? More precisely, they agree on what happened before. what happened before, what happened after. So we really have what's called the happens before relationship. Okay. And they all agree on happens before. So we have some kind of ordering. So A happens before B, and everybody agrees that A happens before B. Okay. And that's what we want for synchrony. Okay. So for example, you have a distributed system. Let's take, again, let's use Facebook as an example, or we can take Wikipedia as an example. I have a page, and then I edit it, right? So the page is hosted on some server somewhere, and there is somebody editing it from some other server somewhere else. We want to make sure that the edits happen in sequence. So the first edit happened, and then the second edit happened, and third edit happened. Right? We want to have that sequence preserved. So that's the happens before relationship. If we don't have it, then the edits are going to be completely out of whack. Right? It doesn't really work properly anymore. Okay. So how many have used the Google Docs with simultaneous editing? Okay. One. Few people have used it. So you know what it's like, right? You're editing something and somebody else trying to edit the same thing at the same time. It's super important that you have the same ordering. Otherwise, it doesn't make any sense. Even with ordering preserved, it still doesn't make sense sometimes. But without that, you're out of luck, right? So we want to have that synchrony property, and that's very important over here. Okay. Any questions on synchrony? Yeah.
So that's what allows you to go back to revert changes.
Revert changes, more importantly, we all see the same order in which we're reverting changes. So if you make an edit A and I make the edit B, we all agree that you made it first and I made it second. Okay. Yeah. Okay, transparency. So transparency means basically transparency has to do with the implementation. Okay. What transparency says is that the services provided by the system are independent of the implementation. Okay, so I have a service, and I don't really know how it's done. Okay, that's transparency. Okay. So. And to give you an example of this, let's say I have a room over here. Okay, there's a physical room. And I have one wall like so. Okay? All right. And I have a person over here who's looking out of the window onto the scene outside. Okay? If that's a perfectly transparent glass window, okay, the looking through service, okay, is independent of the implementation. I can replace this perfectly transparent glass window with a perfectly realistic video screen. Okay, and if I do that, this person can't tell the difference. Okay, so an observer who's looking at the system using that service, looking through service, cannot tell whether it's actually a window that they're looking through, or there's no window at all, it's just plain air, or there's a video screen. Okay, and all three should look the same. So imagine this wall over here. It looks like a bunch of bricks, but if you come up close to it, you find actually it's not bricks. It's actually a big video screen, okay, which has the ugly yellow pattern on it. That would be a transparent brick wall. Okay, transparent implementation of a brick wall. It's not quite transparent, but it's a transparent implementation. So the service over here is a yellow brick wall service. And it's independent of the implementation. I can implement it with actual yellow bricks, or I can put some video screen over there, or I can make a set from a canvas, right? And that's transparent. I can't tell the difference, right? And so that's what transparency means. And it's important to have this because if you make it transparent, you can change the implementation, and the person they don't even know that's being changed, right? So to give a more specific, how many of you have used a virtual machine? Like a virtual Windows, a virtual Mac. Right? So many of you have used virtual machines, right? So what you have there is a transparency of the implementation. So when you start your Windows on your using VMware or whatever software you use, the programs that are running on it don't know that they're running on a Mac. They think they're running on Windows, okay? Because what's happened is that we've transparently implemented Windows on top of the Mac. That's the transparency part. So we can take that portable Windows thing, put it anywhere, and we can't tell the difference because the implementation are independent services. That's what transparency gives us. And a distributed system with transparency, what that means is I can change the stuff underneath all the time, and the users of the service don't even see it. Okay, so it's a very nice thing to have. Again, to give you an example of this, the servers that are being used for Google are changing all the time. Google, when they have a data center, when they have 100,000 servers, they have about 20 to 40 failures every day because the mean time between failures is about 3 years, right? So basically, every day, 20 servers are just dying. So they have a person whose job it is to go around removing all the dead servers, okay? Because they're just piling up every day. However, the service is independent of the implementation, so you never notice it because of transparency. So that's one reason why you have transparency. Okay, finally, we have these two things, performance and heterogeneity. Performance basically means it should have good performance, whatever good means. So you typically have, for performance, you have some metric, you define the metric, and you want the metric to be in some range. So everything depends on what the metric is. So it could be throughput, it could be time between failure, it could be round trip delay, it could be whatever. So you define the metric and you want to have a particular metric. And of course, this metric is going to depend upon the faults, okay? You typically say when there are no faults, this is what happens when you have faults. Well, we don't know, okay? And finally, heterogeneity means that we have an implementation where we can use, we don't have to use all of the same thing. We can actually combine things together in different ways. So if you build a network, it's not necessary that all the routers should be from Cisco. I can take Cisco routers, I can put Huawei routers and Juniper routers and hook them up and it'll still work, right? So that would be heterogeneity. And that's a good thing to have. If you don't support heterogeneity, then you're going to be in a problem where you have a single vendor defining what it is and you must have that vendor. So IBM used to be like that. If you had a network, all the computers and all the routers and all the terminals, everything had to be from IBM and it would work. If you put anybody else's system in there, it wouldn't work. And so, well, that's nice if you're IBM, but it's not nice for anybody else. We'd like to have support for heterogeneity. Okay? And the way we do it is very straightforward. We define the interface, and we say, okay, that's the interface. We don't care how we implement it. And so this kind of transparency also gives us support for heterogeneity for the most part. Okay, I have a few minutes left, so I'm going to briefly discuss locking, and then we'll probably will come back to that later. But I'm going to just show you what problem with locking is. Okay, so we are changing gears here from what are the motivational properties to one specific tool we use, and we use this tool for basically for atomicity. Okay, and this is a tool called locking, or a technique called locking, and it's again a very large, big topic, many different aspects to it. I'm going to focus on just one part of it, and to think about it, I'm going to remind you that we have this problem of concurrency, where we have multiple endpoints or multiple threads of control which are all trying to access some shared element, okay? Shared element. So you have concurrency plus sharing. That's what leads to the need for locking, okay? So to be more precise, let us say that we have two processes that are both trying to access the shared state. Concurrency because you have processes. Oops. And the shared state is number of tic-tac-toe players. Okay. So when a process starts, it wants to increment the number of tic-tac-toe players, right? Because it's a player. And when it ends, or a thread ends, it wants to decrement the number of tic-tac-toe players, right? So it's shared because everybody has to agree, there should be consensus that this is the number of players. So the way we do it is that we define the shared state, okay, and we put a lock around it. Okay, that's a lock. And before you can change that shared element, you have to own the lock to it. Okay, so you've got to have the key to it. So the first person, basically, the first process grabs the key, this process P1, grabs the key, opens the lock, goes in, and basically either increments or decrements the number of players, okay? And then locks it again and puts the key away, okay? The second process comes in, gets the key, and does that. Suppose the first person has the key and the second process comes, try to access that. What will happen is it won't have a key. So it will say, oops, no key. What am I going to do? Well, what I'm going to do is I'm going to wait for the key to come back. Okay, it's called spinning. So you sit there, wait for it. When the key comes, you say, okay, now I can open the door, change the variable, lock it up again, and so on. So this lock and key metaphor allows us to see how we could actually implement locking. And so what we do is we essentially use some way to define a piece, what's called a critical section. This room is called the critical section. And we're going to synchronize. We're going to make sure that all of these processes must have a key to the lock before they can access the critical section. And essentially, you can do this in Java by using a synchronized primitive. You can do that in C#. You can do it in C or in P threads. You need to use a lock primitive, a mutex primitive. And I'll discuss those in class next time. But this is the general idea of what a lock is all about.